Yeah, hi, welcome to another video. In the last video, we started adders and we look at carry propagate adder. And today we will do a little bit of revision of that, and we will look at the disadvantages of ripple carry adder, the problems, the issues, and how we can improve that adder with a carry look ahead type of structure. So let's get started. So if you look at this is a symbolic diagram of an adder. Okay, you have A and B that can be of different different bit sizes. Then C in is single bit, C out is single bit, and some will be the same number of bit as these ones. This is overall, of course, when we go into the individual block diagram of it, each there are a single bit adders connected together. All right, so we already look into that. Then we look into ripple carry adder. Ripple carry adder, what happens is the chain of full adders are connected together. So you have the, for example, 5-bit adder has like a bit 0 full adder, bit 1, bit up to n, and then -1. So just a generalized way of saying that, okay, this is how things are connected. The carry output from each stage is connected to carry input of the next stage, and so on until the last carry out from the last stage, nth stage, right? For example, if it's a 5-bit, then it will be 4. That comes out along with all the sum bit that represents the complete addition. Okay, we look at a structure of a single bit full adder like this, where you have carry in coming here, carry out going there, A and B come here, and the sum is here. You will see in a lot of literature this block diagram is a little different. I just use a very basic one as a sum of min terms, but very soon we will add another exclusive R, and we will understand how we can do that. How is that a correct implementation too? But right now, let's stick with what we came up with last time. This was exactly the structure we came. Then question is, okay, in our example of 5 bits, how the 5 full adders are connected together. Now we are going from generalized block diagram to a particular example of 5 bits, which is important. I feel that in a lot of books are very generic statements of block diagrams are given, but we need to have an example to see how this works. Okay, this is 6 bits actually. So this is 6 bit, n is 6. Okay, general block diagram, 6 bit, 6 bit. Okay, 6 bit is sum, and then 1 bit carry in, correct? This is how these are connected. Carry in comes in, carry out goes out from the last one. Each carry output is connected to the next carry in, on and on and on like that. Okay, what I did now, the full adder circuit that I was showing over here, just put that inside each of them, just to show you how things are calculated. So if you look at this full adder needs to have a stable carry in before its sum is valid and C1 or C out of the first full adder is valid. So it needs to wait for this one. This one's carry C0, which is output from the first and input into the second one, is generated through what? Through the signal coming here, A, B, then they propagate here, carry input comes here, and then this variable. Similarly, this one also goes through this, right? So each stage has to wait for carry in the previous stage. Some will also take over time through this, but once these are present, some will, after this delay, some will be available there. But the critical path critical path means when this all these outputs will be stable. Okay, S0, S1, S2, S3, S4, S5 will be stable as soon as these input comes and the signals propagate will simultaneously propagate to sums, right? But for the C out of this one, this need to travel all the way and has to this initial C in has to travel all the way. Okay, we'll keep changing for a while. Now if you keep this stable and this stable, after a while this will settle down. And that's really determines the time that it takes for all these outputs to be stable. And that is really the time, the delay of the adder. So you can run it on a certain frequency when you want to. Well, we'll talk about the frequency and the storage sequences for later on. But that's important. When outputs will be settled in, stable, for you to use them in the next stage. If those are changing, so you can't use them in the next stage. And that is a key factor there. Okay, so I think I mentioned the same thing here. Question is there a way for you to make this output be stable or come earlier on? Is there a way? And that's where comes our next step of block. Key thing is, if we want to calculate C5 quickly, then first what we have to do is we have to write this one in term of CI. So what happens is, and then this one in term of CI. So some sort of logic that we create that when these inputs come and then you have a carry comes, this circuit can predict the carry output. Or in other words, instead of waiting for this chain action to happen, it can calculate it quickly once the input carry and inputs are available. That's really the key. How to calculate it quicker and faster. So we will use some techniques, you can call it, or it's already there. Every information is already there. We just need to be a little bit intelligent and smart in terms of how we pick some of the outputs. And we basically need, as I said, we need to write an equation for each carry, right? Carry 0, carry 1, carry 2, in term of course, all the inputs and the carry in. Okay, what am I doing here? So what I did just for our example, typically what happens is, and that's the other thing you will see, sometime I look at a lot of videos and books to understand how people are explaining this, because even for me it was a little tricky to remind everything on others. But key thing is that even this technique of carry looker header, what you do is you take a bigger, like let's say 32-bit adder, and then you create it into smaller blocks. Within those smaller, you use carry look ahead, but when those blocks are connected together, you connect them in a more like a chain or ripple carry adder. We will look at that at the end as an example. But right now what I'm doing is, instead of doing all that, also to make my example simpler, I'm just using just 6 bits. I'm just ignore this part, just block 0 what I call. We will look into that. How we come up with those equations? Let's look at that using this example. First of all, we need to look at the truth table and tell you the two important things what are used in carry look ahead. One is generate, the other is propagate, which means for what combination of A, B, and C input a carry is guaranteed to be generated, means guaranteed to be 1. And for what combinations carry output becomes exactly like carry input. In that case, in that moment, we can say it's just moving or propagating carry into output. So if we know these two scenarios, then we can predict that a full adder will for sure have a carry output 1. Again, what are those scenarios? Let's look into them. First of all, look at the scenario when a full adder is guaranteed to generate a carry output, or 1. If you look at carry output as 1, I'm using the same address table that we discussed in previous. And if for those who haven't looked at it, you can quickly add them and you will see like 0 0 0, of course 0 0. This one sum is 1 but carry is 0. Let's look at this scenario. 1 and 1 you add, your answer is 1 0. So you put 0 in sum and 1 is carry. So if you look at for the case when A and B are 1, whether carry input is 0 or 1 doesn't matter. C out is 1. Okay, so for this scenario we call it as a G scenario. Carry is generated from that order. For what? When A and B are 1. Or in other words, we can say when, I think I explain it here again. When AI, BI both are 1 means the AND operation of A and BI is 1. CI, the carry output, which just want to make sure it's not confusing. Is not the input, okay? I mean for that particular column of full adder, ith columns, so output of ith column. So it's basically, maybe I should not, maybe it is basically output is definitely 1. And those are scenario, okay? All right, I think I've explained this. Or in other words, when A and AND of A and B is 1, carry out is generated. Carry out is A and B. So we have taken care of this and this. Now what about these two? Okay, let's look into that scenario. So what happens is, for when A and B is 0 and 1, 1 and 0, and those are here, and those are, oops, right? You need to look at both scenarios. When you look at this scenario, 0 to 0. But what we see from the pattern is actually C input is also 0. But we are not sure. Let's look into again the same combination. When carry input is 1, carry output is 1. So that's an interesting observation that, okay, seems like when A and B are at the 0 1 or 1 0, output is, or carry output basically propagates carry input. It's the same, it's exactly similar to carry input. And then can you think of when 0 1 1 0, for what combination of A and B, what type of pattern, which logic gate represents that pattern, and output becomes 1. So it's an exclusive OR gate. So when A and B type of exclusive OR combination, which is always 0 1 1 0, means either AI, BI is 0 1 or 1 0, then carry out is equal to carry in, means carry is propagated. And this is exactly what is coming. So carry out is supposed to be 1 when A and B are both 1, or this is OR, just sign of OR logic gate, okay? Remember, sum of product terms. Then when AI exclusive BI, now we cannot skip this one because AI and BI exclusive, those are ones even when this is 1. But by putting CI is what we ensure that, okay, let's say these are 0 and 1 or 1 0, then this term will be 1. But then depending upon CI, if it's -1 means the input. Okay, depending upon the carry input, if this is 0, this whole thing becomes 0. If this is 1, this whole thing becomes 1. So that's where the advantage of that. So the two important terms in in this equation are this and this, G and P, generator and propagator. So you can also write this equation as C G. Let's say is the ith column of a large full ladder. So we can say that I, G is I, mean a particular AI, BI. Then PI mean AI, exclusive or BI. And then you a previous carry, right, which I minus 1. So that's how really if you want to make a general equation. Understood so far? This is the block diagram representing this. Let me make sure I create a C, call it CI, and I call it CI. Look at this diagram and figure out whether this is exactly this or not. This is really the key equation, a block diagram or a logic diagram to understand carry look ahead equations. So look at here. So we have A, I just want to make sure this picture is exactly the same as this. So AI, BI is our input for a particular column of adder. What I mean is when you have multiple adder, this is one column, this is one column. Let's go up. Oh yeah, sorry. This is one column, this is one column, this is one column. So in the 3-bit we have 3 columns. And 6-bit we have total 6 columns. That's what I mean by I. So what happens is, let's I, BI, then CI minus 1 because it's previous carry. Sum is equation the same as before. It's an exclusive OR of A, B, and C. So your A and B comes here, the exclusive OR here. Then you have another exclusive OR. One input is coming from the previous one, and the third one is the previous carry. Understood? Then let's look at the C output. C output looks at first it was okay. So think of that it is eventually an OR gate, the final one. Let's go from the final back. OR gate between this and this. Now this one is just AND between A and B, AI and BI. So we bring AI, BI and AND them. So this is your that generate AI, BI. It goes to an OR. The other input of OR is an AND between AI exclusive or BI and CI minus 1. So this output is already AI, BI, which we use in some case. So we will reuse it as opposed to creating another gate. And it's AND here. So this is the P coming here, propagate. But it's AND with the CI minus 1. And this is what you would see typically the equation for our logic diagram for a sum and carry. Hopefully this is understood. Okay. Let me take a look how much we have. All right, not much. So we can finish it in this way. This concept is very simple. You might get confused with different type of videos. People explain different, but concept is super simple. Okay, now remember this equation. Using this equation in this original example that we have, the 3-bit, we will write C0, C1, and C2 in terms of C in. So I'm sorry, sometimes I call it this and that, but you know, these I's were more like individually, but now we are using this particular example, so we can call them a specific subscript. So we need to calculate C0, which is already we can calculate in terms of A0, B0, and Cn. Then C1, we can calculate in terms of A1, B1, and Cn. And C2, we can calculate in terms of A2, B2, and Cn. That's why as soon as Cn comes, we will calculate the delay. But using that equation, we can combine them in such a way that our delay is less than this propagated delay here. Now, of course, if these are just 2-bit, you probably won't see the benefit of this scheme. The bigger this is, the more advantageous you will find carry look ahead of. Okay, C0, as I said, I'm following this equation, not this equation. Okay, so C0 is G0. Okay, then P0 is I, and Cn, Ci minus 1 in this case is Cn. Okay, it's already in term of Cn, so C1 is G1, generate of A and B, P1, A and B exclusive OR, and then multiply with C0, which is the input. Now this equation is not in terms of Cn, so let's expand it. And the value of C0 we can get from this equation. So just substitute that here, and then just expand this further. G1 and P1 you multiply with G0, P0 multiply with P, so it becomes like an AND. So we have two AND gates. This is 2 input, this is 3 input, and we just add them together. Okay, let's look into C2. And I put the whatever G1 and G2 and G0 and P0, P1, P2, they are. C2 is again simple, G2 plus P2 plus C, multiplied with C1 or AND of C1. Sorry, whenever I say multiply, that means ANDing. And now expand the C1, you can put this entire value of C1 into this equation. You get this one, then you P2 multiply with everything here. You just open up this equation and this will turn into something like this. Do it yourself and see you get similar things or not. Let me check. Sometimes I make mistakes. P2 G1, P2 P1, P2 P2 P1 P0 Cn. Okay, so this one is a 4 input AND gate, 3 input AND gate. So there will be some delay differences between a 2 input gate and 4 input gate. There will be some differences. This is much better. We will look into later on when we go into CMOS how different inputs impact the delay through a gate. So now at least the great thing is, look at this. We can calculate C2. Right here, it doesn't have to wait for all those inputs, but we need what? AND gate. So let's put this over here. So now look at this example, C2. That's the most significant bit. I picked just 3 bit. You might say, oh, this doesn't look that much quicker than the channel, but I think you make it 4 or 5 bit, you will see the advantages there. So look at C2. So again, we have 3 full adder. I am drawing the block diagrams inside for both sum and carry. So carry output, look at that. So we have we have A2, B2 coming in, right? Similar to this, let's keep this in mind. It's just moving this whole thing upside down. So then we have exclusive OR gate coming here. Then we have this AND gate, which is this guy. Then we have, for carry output, it's like a 1, 2, 3. So an OR gate with 1, 2, 3, 4 inputs. So this OR gate with 4 input. And G2 comes as is. P2, G1, they come as ANDing together. Then P2, G1 comes as another term. P2, and then comes another one. So we have this result in like a 3 stages. As soon A2, B2 is available, we can calculate G2, P2. As soon these are available, these inputs will come here. I didn't do them, but they will come from here. So it connects to P2 and G1. So G1 is here. Then P2, P1, G0 is here. So basically you will have wires coming from here. But the key thing is, once you have this, the next stage, these will be calculated parallelly, right? And then once these are available, then this will be calculated parallel. So for each column, in 3 stages, you can calculate the output as compared to our previous scenario of this one. We go through this, then this stage, then this stage, then this stage, then this stage. So how many stages are there? It's like 2 from each full adder. But even, for example, if I do C5 here, so you will see that stages, number of stages will be still 3, but what will happen, the complexity, I mean, nothing comes for free, right? So for C5, this is C2, and you already seen an AND gate with 4 input. So for C2, the 4 input, and you can see that for C5 will be lot more input, so it will be a much bigger gate. So of course the delay will not be same as these guys. So um, it will have some bigger delay, but you see the point, right? It doesn't have to wait for 7 8 different stages to have the results. Some is calculated in the same way, like we have a p2 comes from here, carry comes from the previous stage. But once these are available, right, this is the longest one. By this time you will have these one available too. So you got the benefit, right? The benefit is instead of chain thing, you create some sort of parallel, so your number of stages are at least reduced. Now it's a compromise. If you do it like this one, yeah, probably you will still have like 5 6 gates here, and now you have 3, but some are bigger. I don't know. Probably you will see some advantages in this scheme, but not sure how much. But if you make this bigger, then we'll see more advantage. But you must be thinking like if it's a 32-bit adder, like it's a 32-bit CPU, then it's adding 2 registers. Registers contain 32 bits in each register, and then adding them together. Then what will happen to this? How many inputs it will have, right? 32 bits. That would be a huge, and then also OR gate. So it's not practical like that. So what you do is you have a bigger block. As I say, I'm using the same example that. So what I'll use, I will use carry look ahead for the certain number of individual blocks, and then connect these blocks together in like a ripple carry fashion. So of course this one, all these come available, but this one has to wait certain for this one, and similarly the other one has to wait. For so a little bit additional delay from here. But I think that is manageable. As you can see, that it's not like it has to go through a lot of cells. So yes, this will be available for this block. You need to have this thing available. So it will be like a delay of this one, kind of like your starting point. So once after this 3 stages delay, you have this one available only when this will be valid. So there is a ripple carry effect, but at least you have minimizes to some degree instead of doing it for every bit. Hopefully this was clear. Hopefully I've explained well. I intentionally wanted to spend some time on it because later on in computer architecture videos, we will go through developing a microarchitecture for initially MIPS and later on for RISC. So let me know if you have any questions on LinkedIn or as a comment here, and yeah, keep your feedback coming. Thank you so much. Have a wonderful day or night.